Time to conclude the lecture, so please go ahead and fill out your takeaways and your muddy points so that we can better identify how to help you with this in the future lectures. What we definitely want to do together real quick is check our final checkpoints and talk about the conclusion of everything we touched upon in this lecture. So first of all, we talked about rigid bodies and how they are held together really by internal forces. And that is true anywhere along the axis of the rigid body. So hopefully we can agree on that. I believe we can both check it off. Then you understand that there are three forces really in a 2D system, and those are the normal forces, the shear forces, and the bending moment. And of course, we fully understand what those are now, at least conceptually. So I can check that off too, and you can go ahead and do the same. Then we talked about this thing of a virtual cut, right? So you understand that you can always virtually cut any rigid body at really any point. Of course, we did it at very specific points here, but the reason you do that is because you want to release the internal forces. And by doing that, you really turn them into external forces for which you already have all the mathematical knowledge to solve for such external forces. So the internal forces are really not calculated any different than the external forces. They just named differently, and after you cut them, you effectively have an external force that you then can solve for using the cantilever method. Then we are aware that we have a precise definition for each of these, right? So we don't randomly assign internal forces. We have a positive shear force, a positive normal force, and a positive moment. And they are very specific to their orientation. And that relates to the reference fiber. We obviously understand that because without the reference fiber, we could not properly assign them. So let's check that off. Then we need to understand that the positive internal forces always act in the same direction as the predefined ones, right? So this is something that was inherent to what we talked about. So the predefined is really what you have on your little study card. And if the value come out to be positive, then it goes in the same direction. If the value comes out to be negative, then it is actually opposite to that. However, you will never flip around the forces here. You will always keep them positive or negative. And that will become more clear as we go through further lectures. But for now, we understand that there's a predefined positive and a predefined negative. Now, what you also need to be able to do to solve these problems is to properly draw the free body diagrams that include all the known forces, and known forces are the external forces, including the support reactions. But you also need to bring in your three unknowns, the internal forces. And that is what really helps you to solve the problem. So we can shake that off too, because you understand that. And then last but not least, you understand that you can solve for internal forces by using the equilibrium equations or the conditions, because we understand that the unknown forces are really nothing different than the forces that act on a fixed support. So you can really use your knowledge from cantilever beams to find these internal forces, as long as all other forces, and that means external forces, on the subsystem are known. And I believe we can agree that this was definitely shown in this example or in this lecture, how you have to do that, at least for a simply supported beam. And of course, in future lectures, we're going to talk about more there. But for now, I think we can conclude the lecture, and we know now how to apply our knowledge. Of course, you can practice this more through your homework. So let's go ahead and decipher the homework on the next page. All right, let's discuss everybody's favorite page, the homework page, for which we usually end up with 6 problems. And here you have to find the answer to 6 problems for the internal forces at a specific location. Let's dive into the first problem, and let's see that we have a simply supported beam that carries 2 loads. These 2 loads are different from one another, although the system is geometrically symmetric, but you have to be careful because the load case is not. And what you're asked here is to find the internal forces N, V, and M at location C. So C is indicated here with that dot. And what that means is you have to find your support reactions first. And after you found the support reactions, you can either release the right side or the left side, bring in your internal forces and solve for those internal forces. And there's really nothing more and nothing less to that. So we can move on to our next problem. So for problem B, it's very similar, except now you're actually dealing with distributed forces on top of that. And please don't get too confused about that. I see that sometimes in the classroom that students initially get confused, but all you have to do is cut through that force as well. So you either release the entire right system or the entire left system, and one of them might be easier for you than the other one, but I'm sure you can figure that out yourself. However, after you cut the system, either side, you just bring in your internal forces and you calculate them like you calculate cantilever support reactions, just by cutting through the system, even through the distributed force. So don't get too hung up on this. Again, I see that sometimes in the classroom, that initially students get hung up by the fact that the distributed force actually passes over the point, but just blindly cut it off on the other side, no matter if you do the right side or the left side. And I'm pretty sure you can solve this as well, because you already solved cantilever beams with distributed forces acting on them. Let's go to the next one. Now it becomes a little bit more interesting. We have actually triangular loads, but again, you also have calculated support reactions for cantilevers on triangular loaded systems. So here you look at something very similar, except now you find the internal forces at location C once again. And once again, you just release the system, either the right side or the left side. In this case, it really doesn't matter because it's truly symmetric. So it's really up to you. And you find N, V, and M as for all of these problems. So there's no real secret here that I can share with you. Of course, this can be challenging initially, depending on how well prepared you are. But I promise you, practice makes perfect in this case. And the more you practice here, the better it will become throughout the class. And you can see that everything in this class actually builds upon each other. And this is why you should definitely put a lot of effort into these homework assignments, because they will also lead you to the next step and to the following topics. Now, once again, a little bit more interesting here, we have a simply supported beam with overhang, and we have a distributed force here, and now you need to find the internal forces at that location. And so once again, you release the system, either the left side or the right side, and you bring in your internal forces and solve for them. So the trick here, similar to all the problems in this homework assignment, is really a strong sketch for your cut and then a standardized approach that I tried to exemplify to you in the lecture. So once you have that developed, I believe you can breeze through these problems with ease. So let's take a look at the last two problems. Now it becomes a little bit interesting, because this is something we didn't cover in this class, internal forces for a cantilever beam. But to no surprise, it's no different after you found the support reactions. In fact, you may not even sometimes have to find the support reactions for cantilever beams, and this is something that you can learn through application as you solve these problems. Because remember, you have to release either the right side or the left side of the system. And so here one side requires you to find the support reactions first, the other one doesn't. And that is a little bit confusing as well. At least that's my experience in the classroom. And it was also confusing to me when I first started solving these problems. But again, practice makes perfect, and you just have to apply your knowledge more and more to really get proficient at these problems. And I promise you that every second and every minute you put into these problems really pays off at the end. And it definitely pays off in terms of your engineering understanding. So this is something we didn't practice in the lecture, but at the same time we did practice it because it's not really that different. And I let you explore that. Then we have a hinged beam here, which, yeah, this may look a little bit tricky compared to what we have done in the lecture, but at the end it's always the same. You just release everything to the left side or to the right side of the location that you're looking for. In this case, we're looking for location D. So you cut the system here after you found your support reactions, and then you go ahead and solve for the internal forces at D. And that now concludes our lecture, and our homework is clearly defined now. I wish you good luck with that. Happy studying. I will see you in the next lecture. Until then, stay safe.